Modern warfare increasingly unfolds across distances that would have been unimaginable in earlier conflicts. Armies no longer operate as single concentrated formations, moving across clearly defined front lines. Instead, forces disperse across vast regions, forming networks of units that must communicate, maneuver, and reinforce one another rapidly. In this environment, the ability to move troops quickly becomes as important as the ability to fight. For decades, helicopters served as the primary solution to this problem. Vertical takeoff allowed them to operate without runways, landing directly beside soldiers in remote locations. They could insert troops behind enemy lines, evacuate casualties, and resupply units operating far from conventional infrastructure. Yet the helicopter carries a limitation rooted deeply in its aerodynamic design. The same rotating blades that allow it to hover also prevent it from achieving high forward speeds. As battlefields expanded and threats evolved, that limitation became increasingly difficult to ignore. Modern air defense systems detect and respond faster than ever before. Radar networks, infrared sensors, and mobile missile launchers can identify aircraft from long distances and respond within minutes. The longer an aircraft remains inside hostile territory, the greater the chance it will be detected and targeted. Speed, therefore, becomes more than a matter of convenience. It becomes a matter of survival. Traditional helicopters rarely exceed cruising speeds of 250 kilometers per hour. That speed may be sufficient for short missions, but in large-scale operations, it can expose aircraft and soldiers to extended risk. Troops transported by helicopter may spend valuable time flying across hostile territory, vulnerable to radar detection and missile engagement. Military planners began searching for a new type of aircraft capable of solving this dilemma. It needed to retain the helicopter's ability to land vertically while dramatically increasing speed and range. The aircraft would have to combine two seemingly incompatible capabilities: hovering like a rotorcraft and flying like an airplane. This requirement led to the development of tiltrotor technology. Among the most advanced examples of this concept is the Bell V-280 Valor, developed by Bell Textron for the United States Army Future Long-Range Assault Aircraft Program. The aircraft represents a new generation of vertical lift platforms designed specifically for the demands of modern warfare. Its purpose is not simply to replace helicopters. It is to redefine how military forces move across the battlefield. To understand why a new design was necessary, it is important to understand the physics that limit helicopter speed. A helicopter's rotor functions as a rotating wing. As it spins, each blade generates lift by forcing air downward. In hover, the airflow across each blade remains relatively symmetrical. But when the aircraft begins moving forward, the airflow experienced by each blade changes dramatically. One side of the rotor disc moves forward relative to the aircraft's motion. The blade on this side becomes the advancing blade, experiencing higher airspeed and generating more lift. On the opposite side, the blade moves backward relative to the aircraft's motion. This retreating blade encounters lower airflow and produces less lift. At moderate speeds, engineers compensate for this imbalance by adjusting blade pitch. But as forward velocity increases, the retreating blade eventually reaches a point where the airflow is insufficient to maintain lift. This phenomenon, known as retreating blade stall, produces severe vibration and instability. At the same time, the advancing blade begins approaching transonic speeds. The outer tip of the rotor may approach the speed of sound, creating compressibility effects that dramatically increase drag. These two aerodynamic barriers form a natural speed limit for helicopters. Engineers can delay these effects with advanced materials and rotor designs, but they cannot eliminate them entirely. The problem lies in the dual role of the rotor. It must provide both lift and forward propulsion simultaneously. As long as the rotor remains responsible for both functions, speed will remain limited. The solution, therefore, is to separate these roles. Tiltrotor aircraft solve the helicopter's speed problem by transforming the function of the rotor during flight. During takeoff and landing, the rotors face upward, acting like helicopter rotors and producing vertical lift. Once airborne, the rotors gradually tilt forward. In this position, they function like propellers, generating forward thrust while wings provide lift. This configuration allows the aircraft to transition from rotorcraft flight to airplane flight. Once the wings take over the lifting role, the rotor blades no longer face the same aerodynamic limitations. Instead of fighting against retreating blade stall, the aircraft flies like a turboprop airplane, capable of much higher speeds and greater efficiency. The concept is elegant in theory, but extraordinarily complex in practice. Transitioning between two flight regimes requires careful control of aerodynamics, power distribution, and stability. Earlier tiltrotor aircraft such as the V-280 Osprey demonstrated that the concept could work. However, engineers learned valuable lessons from that aircraft's design, leading to significant improvements in the V-280. One of the most visible differences in the V-280's design lies in the way its rotors tilt. On the V-22, the entire engine nacelle rotates along with the rotor. In the V-280, the engines remain fixed within the wings, while only the rotor system tilts. This change simplifies the mechanical design and reduces the number of moving components. Simplifying the tilt mechanism improves reliability and reduces maintenance requirements, two critical factors for military aircraft expected to operate in demanding environments. The rotors themselves represent advanced engineering structures. Each blade must generate enormous lift during hover while remaining aerodynamically efficient during high-speed cruise. Composite materials provide the strength required to withstand these forces while minimizing weight. Rotor diameter is carefully chosen to balance hover efficiency and forward flight performance. Larger rotors distribute lift over a wider area, reducing power requirements during vertical flight. However, they must also remain stable and efficient when acting as propellers during high-speed cruise. The wings of the aircraft play an equally important role. Unlike helicopters, which rely entirely on rotor lift, the V-280 uses fixed wings to support the majority of its weight during forward flight. These wings generate lift more efficiently than rotor blades, enabling the aircraft to travel farther with less fuel. The wing structure also carries the loads generated by the engines and rotors mounted at its tips. Composite materials allow engineers to construct strong, yet lightweight structures capable of handling these stresses. The aircraft's fuselage sits beneath the wing like that of a conventional transport airplane. Inside, the cabin is designed to carry soldiers and equipment during assault missions. Wide side doors allow troops to rapidly deploy once the aircraft lands. The result is an aircraft that visually resembles a hybrid between a turboprop transport plane and a helicopter, reflecting its dual aerodynamic nature. The most technically challenging phase of tiltrotor flight occurs during transition. At the start of the transition, the aircraft is essentially a helicopter. Rotor lift supports the aircraft's weight, while forward thrust remains minimal. As the rotors tilt forward and airspeed increases, airflow across the wings begins generating lift. Gradually, the wings assume a greater share of the lifting role. Eventually, the aircraft becomes fully supported by wing lift, while the rotors act purely as propellers. Managing this shift requires extremely precise control. Digital fly-by-wire systems monitor airspeed, rotor orientation, aerodynamic loads, and aircraft attitude hundreds of times per second. These systems coordinate the movement of control surfaces and rotor thrust to maintain stability. Pilots therefore command general flight behavior rather than manually adjusting every variable. The aircraft's computers translate pilot inputs into coordinated actions across multiple control systems. This automation allows the aircraft to move smoothly between hover and high-speed flight without abrupt changes in handling. The result is a machine capable of operating in two fundamentally different aerodynamic environments. And in doing so, the V-280 Valor opens a new chapter in the evolution of vertical flight. At the heart of the V-280's performance lies its propulsion system. The aircraft relies on powerful turboshaft engines capable of delivering the enormous energy required to lift a fully loaded transport aircraft vertically into the air. During hover, nearly all of the engine's power goes directly into turning the rotors. Each rotor must generate enough lift to support not only the aircraft itself, but also the soldiers, fuel, and equipment inside it. As the aircraft transitions into forward flight, power distribution changes. The rotors begin functioning as propellers, converting engine power into forward thrust rather than vertical lift. At this point, the wings take over much of the lifting responsibility. Connecting engines to large rotors requires complex transmission systems. Gearboxes convert the high rotational speed of the engine into the lower speeds required for efficient rotor operation, while maintaining reliability. Power transfer systems also connect both rotors, allowing one engine to assist the other if necessary. This redundancy improves safety by ensuring that the aircraft can maintain control even if one engine experiences difficulties. Unlike conventional airplanes or helicopters, tiltrotor aircraft must remain stable across dramatically different flight regimes. During hover, the aircraft behaves like a helicopter, relying on rotor thrust for control. During cruise, it behaves more like a turboprop airplane, using aerodynamic control surfaces. The V-280 uses advanced fly-by-wire control systems to manage these transitions. Computers continuously adjust rotor thrust, blade pitch, and control surfaces to maintain stability. This level of automation allows pilots to focus on mission objectives rather than managing complex aerodynamic interactions. The most significant advantage of the V-280 is speed. The aircraft is designed to cruise at speeds exceeding 500 kilometers per hour, nearly twice the speed of most conventional helicopters. This increase dramatically expands the distance that troops can travel within a given time frame. Missions that once required hours of flight may now be completed in a fraction of that time. Range also improves due to the efficiency of wing-borne flight. Fixed wings generate lift with far less energy than rotating blades, allowing the aircraft to travel farther while consuming less fuel. This extended reach allows military forces to launch missions from safer locations, far from hostile territory. The V-280 is designed primarily as an assault transport aircraft. Its mission is to deliver soldiers quickly into contested environments while minimizing exposure to enemy defenses. Rapid insertion allows forces to seize key terrain before adversaries can respond. High speed reduces the window during which enemy air defenses can engage the aircraft. Once troops are delivered, the aircraft can quickly depart the area, reducing vulnerability to counterattack. This capability transforms how commanders plan operations. Instead of relying on slow-moving helicopter formations, forces can maneuver across the battlefield at much higher speeds. Aircraft operating near the battlefield face numerous threats, including radar detection and guided missiles. Speed itself provides a degree of protection by reducing the time aircraft spend within enemy engagement zones. The faster an aircraft moves through hostile airspace, the harder it becomes to track and intercept. Additional defensive systems such as missile warning sensors and countermeasure dispensers provide further protection. These systems detect incoming threats and deploy flares or electronic interference to disrupt missile guidance. Together, these measures increase the aircraft's chances of surviving in contested environments. Military aircraft must maintain high operational readiness even under harsh conditions. The V-280 incorporates design features intended to simplify maintenance and improve reliability. By keeping the engines fixed rather than rotating with the rotors, engineers reduce mechanical complexity. Fewer moving parts translate into fewer potential failure points. Modular components allow technicians to quickly access and replace systems, reducing downtime between missions. Digital monitoring systems track the health of critical components during flight, allowing maintenance crews to identify potential issues before they lead to failures. The V-280 Valor represents a significant step forward in rotorcraft technology. By combining the vertical flexibility of helicopters with the speed and efficiency of airplanes, it expands the possibilities of military mobility. Future aircraft may continue this trend, integrating advanced materials, improved propulsion systems, and even autonomous flight capabilities. In a battlefield defined by speed and distance, the ability to move forces rapidly without relying on runways will remain essential. The story of the V-280 Valor is ultimately a story of engineering innovation. By rethinking the relationship between rotors, wings, and propulsion, engineers created an aircraft capable of overcoming the limitations that constrained helicopters for decades. It is neither purely helicopter nor purely airplane. Instead, it exists in a space between the two, drawing strength from both. In doing so, the V-280 opens the door to a new era of vertical flight, one where speed, reach, and flexibility combine to reshape how forces move across the battlefield. And in that evolving landscape of modern warfare, the ability to arrive quickly and precisely may prove as decisive as any weapon carried into battle.